back. So let me remind you, x and y be two sets. A function f from x to y is said to be bijective if f is both injective and surjective. So notice, function means every element in x has one and only one association on the right. That is, every passenger has one and only one destination to go to. No passenger is left behind. Everyone has a place to go to and one and only one place to go to. That is a function. Injective means different passengers go to different destinations. Different passengers go to different destinations. Surjective means every destination is achieved. All right. Bijective means both injective and surjective. The purpose of bijective functions, if I reverse my arrows, then I get a function again. All right. And the reverse function is also bijective. So notice, if I reverse the arrows, not only do I get a function, I get a bijective function. Okay. Now, geometrically, suppose consider R the set of real numbers, and you take your x inside R, subset of R. F from x to R be any function. So this is what is called a real valued function. It takes the image of f is inside the set of real numbers. Okay. So take f any real number. By the graph of a function f, of this function f, we mean you look at set of points in the coordinate plane xy where the y coordinate is given by f of x coordinate. So consider the function fx equals 1 over x. So y coordinate has to be fx. Fx is 1 over x. So for each x, you're associating y, that is 1 over x. Notice, this function is not defined at 0. So the domain is everything except 0. So open set negative infinity to 0, union, open set 0 to infinity. And this is the graph. So y coordinate is calculated by plugging in x coordinate in my function value, in my function. That's how you find the y coordinate. So that's your graph of your function. Now, what is the vertical line test? Well, every vertical line drawn in the domain intersects your graph exactly once. That's when you know your graph is graph of a function. Okay, so here is the graph y equals fx, that's 1 over x. Any vertical line, here is an example, one vertical line. It meets the graph only once. If I move the vertical line to the right, it will meet the graph only once. Notice the vertical line should be on your domain. Otherwise, in the domain, notice this vertical line does not meet my graph. Right? So you have to be in the domain, your vertical line. Then you notice it will hit your graph only once. Here is another graph, y equals fx, that is x squared, y equals x squared. Every vertical line meets this graph only once. So that tells me my function, my graph is graph of a function. Why does that say? It says for every x, there is one and only one y. All right. For every x, there is one and only one y. That's why it has to meet your graph only once. So vertical line test is the test to determine whether the graph you are given is that of a function. What about horizontal line test? It is a test for injectivity or one-to-oneness. You take a horizontal line. That means for every y, there is one and only one x. That makes it injective. That is, no two x's will give you the same y. No two x's give you the same destination. So y equals 1 over x, that one is indeed injective. On the other hand, fx equals x squared. Here is an x, here is an x. They both have the same height. See, horizontal line meets my graph in two locations. That means there are two different x values which give me the same y coordinate. So horizontal line test fails here. Horizontal line test passes here. So this function is injective. This function is not injective. So you see, fx is x squared is not injective. For example, f at -1. Well, I'm squaring it, gives me positive 1. F of 1, I'm squaring it, gives me positive 1. So x values, there are two x values with the same output, same y value. So that's where it is not injective. So horizontal line test is to test injectivity or one-to-oneness, okay? Now let's start with the definition of an inverse function. Let f be from x to y be a bijective function. You want a bijective function. Then the inverse function of f is denoted by f power -1. So it's inverse function. You read it as f inverse. Is a function from y to x. F inverse of y is x if and only if f of x is y. If f is an injective function, notice, if f is not bijective but just injective, then you can still define the inverse. But at this point, you're going to take range y to x because that is your domain now. Okay? Definition is the same. F inverse of y is x if and only if f of x is y. So if I'm going to start from here, I see which element from here maps me. I go back. Okay. So now we are going reverse. So from a destination, you go to the passenger. All right. One thing to note, domain of f is the range of f inverse. Range of f is the domain of f inverse. So range and domain interchange. So this is the definition. In general, how do you find the inverse of a function? Well, first set y equals fx, solve for x in terms of y, exchange x and y. Okay, only 3 steps. Step 1, set y equals fx. Step 2, solve for x and y, solve for x in terms of y. Step 3, exchange x and y. Okay, that's how you identify the inverse. For example, example 1, consider the function fx equals x to the power 3. Identify the inverse. Well, first set y equals fx. In our case, y equals x cubed. That's step 1. Now you want to, step 2, solve for x. As y is x cubed, how do I solve for x? Well, I need to take cube root. X equals cube root of y. Step 3, interchange x and y. So where I see x, I place y. Where I see y before, I place x. Y equals cube root x. This is my inverse function. F inverse x is cube root of x. That's it. So inverse of power 3 is cube root. Here is another example. Identify the inverse function of fx equals 3x plus 4 over 2x minus 5. Step 1, set y equals fx. Step 2, solve for x. I need to solve for x in this equation. So that's my equation. Let me clear the denominator, that is multiply both sides by 2x minus 5. That clears 2x minus 5 from the right. Distribute the y. Okay. Now, I will move the x's together on one side. Remember, the goal is to solve for x. So I'll bring the 3x here, move the 5y there. Negative 5y became positive over there. Positive 3x became negative 3x here. Now here I can factor x. 2y minus 3 is 5y plus 4. Okay. Divide both sides by 2y minus 3. And there you have x equals 5y plus 4 over 2y minus 3. You have solved for x. Now interchange x and y. Where I see x, I write y. Where I see y, I write x. Everything else the same. The right hand expression now is the inverse. So the point is, now look at the graphs, right? You know how to draw the graphs of fx or any function. You are saying y coordinate is the value you get by substituting x in the function, be it the function or its inverse. Well, it turns out graphs of the functions of f and f inverse are reflections of each other about the line y equals x. You take the line y equals x, graph of fx and graph of f inverse x will reflect about each other. Well, what's the advantage? If f is continuous, that is the graph of f is not broken, then the graph of f inverse will also be not broken because they are reflections. In other words, if f is continuous, so is f inverse. Okay, that's an important point. Which brings us to the last theorem, how to find the derivative. I will continue this in our next video. Until then, bye.